Hello students, today we will discuss work from the chapter Work, Energy and Power of 11th standard. The meaning of work in physics is different from the common language used in daily life. In physics, work is said to be done if a force acting on a body is able to move it through some distance in the direction of force. So, work is a scalar quantity. It is measured in joule or Newton meter. The dimensional formula of work done we can find out. If you don't know the dimensional formula of work done, we can find out here. That is, the product of force and displacement is called work done. So force has a dimension ml raised to minus 2 and displacement is measured in L. So this is ml square t raised to minus 2 is the dimensional formula of work done. Now, how will we calculate work done is it is the product of component of force in the direction of movement of this body. For example, there is a body M here. Okay, this is having a mass M. It is moving from the position A to the position B. Let us imagine that is AB is a distance D given in the figure. So the force applied is like in this direction, that is F. Okay, we will do the calculation of work done. Work done is force into displacement. Which force we will take? The force which is acting in the direction of displacement you have to take. That is this force you have to take. This is called F cos theta. So we will find work done as the product of F cos theta into D, which is nothing but Fs cos theta or Fd cos theta. In this figure it is D given. So it is Fd cos theta. So F and D, these are the magnitudes of force and displacement, and theta is the angle between the force and the displacement. The displacement happens in this direction. So theta is the angle between F and D. Here F is the modulus of the force, vector force, and D is the modulus of the displacement D. Work done is, as I told you, it is a scalar quantity measured in Newton meter or joule. Okay, Newton meter, or we can write it as joule. 1 Newton meter is 1 joule. Dimension we already found out, ml square t raised to minus 2. Now work done by a force is 0. The condition is the displacement may be 0 or the angle is 90 degree, meaning the displacement of the body is perpendicular to the force applied. Now work done by the force is positive if the angle between force and displacement is less than 90 degree. Work done by the force is negative if the angle between the displacement and force is obtuse, that is greater than 90 degree. So for a small angle, the work done is positive. For bigger angles like above 90 degree, the work done is negative. And if the applied force is a variable force, the formula we have to use is W is equal to F dot integral F dot ds. As we discussed, there are 3 different types of work done possible. That is positive work done, negative work done, and zero work done. So positive work done means displacement and force both should be in the same direction. That is what is meant by the angle theta is equal to 0. If the displacement and force are in opposite direction, that means theta is 180 degree, it is said to be negative work done because the product will give you minus Fs. Here the product is plus Fs. If they are perpendicular, the force and displacement are perpendicular 90 degree, what will happen is this W is equal to Fd cos 90 we will get. As you know, cos 90 is 0, so the work done will be equal to 0. The graph of work done, force and displacement for a constant force is like this, a straight line. Okay, so a straight line graph you get when you plot f cos theta and d or s, whatever you call it. So this like a graph, a straight line graph we get because it is a constant force. So how to find the work done is you find the area under this graph. This will give you the work done. Area under the force displacement graph gives you work done. Okay, so work done by a variable force can be found graphically. That is, what you have to consider is the body moving from xi to xf under a variable force. The variation of force with position will be as shown in the figure. Consider a small strip of displacement delta x. The force in this interval is nearly a constant. Hence, work done to move a body from A to B can be delta W, which is equal to Fx delta x. So I'll write here that to move this distance, the delta W, that is the small amount of work done required, is F of x delta x. This gives the area of the rectangle over there, that is this shaded rectangle over here we will get. And when we add successive rectangular areas, that all these successive rectangular areas, when we add, we get W is equal to sigma f of x delta x, or when we take delta x tends to 0, this delta x we are taking a very small distance, that is not this much considerable distance is there, infinitesimally small distance if you are taking, then W can be written as integral f of x dx. So anyway, the area under this graph will give you whether you find the sigma or integral. What we are doing is finding the area under this graph. This will give you the work done in this case. Next we will see what is work energy theorem. Okay, the change in kinetic energy of a particle is equal to the work done on it by the net force. That is what the work energy theorem statement says. So how will we find out this is true? So we'll take a body of mass m, okay, which is moving with a velocity, initial velocity u, and it attains a final velocity v. Then what will be the change in kinetic energy? We will find out what is the change in kinetic energy of this body. Change in kinetic energy means it will be half m v square minus half m u square. And we know that here half m is a common factor, we'll take it out, so it is v square minus u square, and we can replace v square minus u square by 2as, because we studied in earlier chapter what is v square minus u square is. This is 2as, so 2 get cancelled and we get ma into s. What is m into a? M into a is nothing but the force. So force into displacement you got. So what we found was change of kinetic energy, and we ended up in the work done. So that is what the theorem says. The change in kinetic energy of a particle or a body is equal to the work done by it by the net force. So change of kinetic energy is equal to work done. Next we will see what is work energy principle by variable force. Work energy theorem for a variable force can be derived from work energy theorem of constant force. According to work energy theorem of constant force, change of kinetic energy is work done. So what we can write? We'll write here dk, that is the change in kinetic energy. Small change means dk, you can represent it as, it is equal to dw. This is according to the work energy theorem of a constant force for a very small change of energy. Now if you differentiate it with dt, dk by dt, if you do, you know it will be d by dt of half mv square. Right, so what will we do here? Half is a constant, we'll take out. M is also a constant, we'll take out. D by dt of v square we will do. D by dt of v square is 2v into dv by dt. So this 2 and 2 get cancelled, and what we get finally is m. What is dv by dt? dv by dt is a into this v. So we get it as fv. We can write it as f into dx by dt, because v is nothing but dx by dt. What is the left hand side? The left hand side is dk by dt, isn't it? dk by dt is the left hand side. So we'll bring the left hand side here. dk by dt is equal to dx by dt. So what we get? dk is equal to f dx. So this is our work energy theorem for variable force. If you want to find it for larger value, that is from the limit ki, that is kinetic energy initial to kinetic energy final, we can use the integral formula, integral xi to xf f dx, where xi is the initial position and xf is the final position of the body. We will do a numerical based on what we learned today. The question says a body of mass 20 kg is moving with velocity 40 meter per second, changes its velocity to 60 meter per second in 3 seconds. Calculate the work done by the body. So here what we have to find is the work done. Work done by the body you need to find. This is the question. And we have the mass given, so m is equal to 20 kg. We have initial velocity given, that is u is equal to 40 meter per second. V final velocity is given 60 meter per second. So from this, if you have to find the work done, how will we do work done? Work done is equal to what we studied is change of kinetic energy, delta Ke, according to the work energy theorem. So it is half m v square minus half m u square. So half m is constant, common factor, half into m is 20 kg, v square minus u square you have to do. Okay, v square minus u square. So this is 2 and this one cancels. It is 10 into v square is 60 square minus 40 square. So we'll find out the value and substitute. 10 into 2000. So it is 20 into 10 raised to 3 joules. 20 kilojoule. The answer is 20 kilojoule. A body constrained to move along z-axis under a constant force of F equal to minus I cap plus 2 J cap plus 3 K cap Newton. Work done by this force in moving the body a distance of 4 meter along the z-axis. So find the work done by this force in moving the body along 4 meter along the z-axis. What is 4 meter along z-axis means? Along z-axis, if displacement is there, d is equal to, you have to write 4 k cap. So work done is equal to F dot d. So it is minus I cap plus 2 j cap plus 3 k cap Newton dot 4 k cap. So we know in dot products, only the like vectors you can multiply. All other products will be equal to 0. So it is 12 joule.